In this video, we're going to have a look at the circle theorems that involve cyclic quadrilaterals. So a cyclic quadrilateral is a quadrilateral that has its 4 vertices on the circumference of a circle. So we're going to prove the opposite angles of a cyclic quadrilateral are supplementary. And remembering that supplementary means they add to 180 degrees. So in our diagram, we're basically trying to prove that angle X plus angle Y is going to equal 180. So to complete this proof, we're going to draw in the lines OA and OC. And OA and OC represent the radii of this circle from its centre O. So we're going to say, if we're going to call angle ABC X, then angle AOC is going to be worth 2x. So I'm going to put that in there. And we know that's true because this is using the central angle theorem. Okay. Now we can also say that the other angle AOC around that point O is going to be worth 360, take whatever 2x is. So I'm just going to highlight that in blue. And this is because the sum of the angles at a point equal 360 degrees. What this means is that angle ADC, we have a look, because we've got that angle 360 take 2x, angle ADC is going to be half of 360 take 2x, using that central angle theorem. So we've got a relationship between that 2x and that y. And so this is going to be 180 take x. Now, as angle ADC represents y, this implies that y equals 180 take x. Therefore, x plus y equal 180 degrees. And therefore, we have just proved this theorem, that the opposite angles in a cyclic quadrilateral are supplementary. Another theorem to do with cyclic quadrilaterals is the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now, in our completion of some questions, we're going to actually prove this one. So we've got the cyclic quadrilateral ABCD, and we've got this secant going from B through C to E, and E being that external point. So what I've called this angle BAD X, and we want to prove that this opposite external angle that we've got here is going to also be the value of X. So you might like to, when we get to this question, have a go at it. If not, pause the video and have a go now, considering that if we call angle BADX, how we can define, for example, angle BCD, knowing that we've just proven that opposite angles in a cyclic quadrilateral are equal. One important thing to note for a bit of language is if 4 or more points lie on the same circle, they are said to be concyclic. So we're going to have a look at a question now. We're going to look at question 1a, finding the value of the unknowns in this. We're going to give some reasons behind each of them. So taking a look at this circle, I can see that I've got a centre point and I've got some radii coming off them, and I've got a triangle that's formed with a chord there. I also know that I've got, from this chord here that I'm highlighting in pink, I've got an angle that is in that arc. So we can essentially call that arc AB, or that chord AB. So from that arc, we've got an angle that's been created 68 degrees. knowing that we've got that centre. So I'm going to say that A is going to equal 2 lots of 68 degrees. So that's going to be 136 degrees. And that's using the central angle theorem. So A is going to be twice the angle on the circumference. Now B and C are going to be the same length because we've got the radii of the circle. We form that triangle AOB. We call that centre point O. So they're going to be taking away 136 from 180 and sharing that out, and that will give us 22 degrees. And because we've got that isosceles triangle formed there from the radii. Now D is sitting over away from all that. So if we have a look here, we've got our cyclic quadrilateral. So I'm going to actually call our cyclic quadrilateral ABCD. I'm going to highlight the rest of that in pink so we can see it. Now straight away, I notice from what we've just proven that I know the size of the angle in total at point A or vertex A. So that is going to be 52 degrees. And D is directly opposite that. And I know that opposite angles in a cyclic quadrilateral are supplementary. So if I take away 30 plus C from 180, which is 180 take 52 degrees, that's going to tell me the value of D. So using the opposite angles in a cyclic quadrilateral, I can say that D will be 128 degrees. So now pause the video and have a go at part 1b to see if you can write a reason behind how you evaluated the two unknowns in that situation. And then have a go at question 2 that says, prove that the points A, B, C and D actually form a cyclic quadrilateral. So think about what we've just proven in terms of the opposite angles being supplementary. We'll pause the video and come back and check your solutions and your proof. So in part 1b, we can see that we've got beta being 35 degrees, and that's because it's an angle in the same arc, and that arc is NR, and we can see that it's the same as the angle at S. And our other unknown is going to be 29 degrees plus beta, and that's because the external opposite angles are equal. So we can see that that's going to be 64 degrees. Now in this diagram, it looks like it should be an obtuse angle. So don't be put off because the diagrams obviously are not to scale. So we can have an external opposite angle. Okay, question 2. We have got this quadrilateral that ABCD with some information, and we want to say that it is actually cyclic. So to prove it's cyclic, so for ABCD to be a cyclic quadrilateral, those opposite angles ADC and ABC must be supplementary, because that's our first proof that we did, first theorem, the opposite angles of a cyclic quadrilateral are supplementary. So if we can prove that one set will be supplementary, the others will follow on to be supplementary. So we can first work out the size of angle B, and we're saying that from that triangle ABC, that angle ABC must be 97. So we want to prove that 83 plus 97 is in fact equal to 180, in which we've done. So therefore it is a cyclic quadrilateral.